All right, let me share my screen. Take a look at the quiz. Okay, so there's this one question: is locate and classify any critical points using the first and second derivative tests. Okay, and we have x cubed plus y cubed minus 3x minus 75y minus 3. Okay, and I didn't write it out. I probably should have. That was f of xy. Okay, so how do we first decide where the critical points are? What's the first thing we have to do?
Find where the partial derivative with respect to x and y equals 0.
Yeah, but I like to say it in one word: the gradient. Okay, so get used to that gradient, because a gradient is like the key to this whole part of the class. So we want to find out when the gradient equals 0. So let's calculate the grad. And I didn't call it f because I didn't have time, but the grad f is equal to, well, you take the derivative with respect to x, and what do you get?
(3x squared minus 300).
So grad f is equal to 3x squared minus 300. Comma, and then you do the same idea for y, and you get 3y squared minus 75. Any questions on that? Okay, we need to set that equal to 0, 0. So to do that, when you have a vector equals 0 vector, that means each of those are 0. So that tells you 3x squared minus 300 is 0. Let's write that out. So we get 3x squared minus 300 equals 0. And we also get 3y squared minus 75 equals 0. Any questions on that? Okay, what are this? So what points do we get? That's going to give us some points. So give me the points that you get out of that.
10, 5.
Okay, good. One of them is 10, 5, but there's more.
And then negative 10, 5.
And there's more.
And then there's negative 10, negative 5.
And one more?
10, negative 5.
Yeah. Any questions on finding the critical points? Let me write critical point. Those are our critical points. Any questions so far? Okay, next thing we need to do is we need to find the Hessian. Okay, and from that we can find what the book calls D, which is the determinant of the Hessian. So to do that, we find all of the partial derivatives and put them in a matrix. So let's go and do that. So let's make a matrix out of it. I'm just going to use a table, I think is the easiest way. Okay, so what's the first entry of our table, of our matrix?
fxx.
Yeah, which is 6x. What's the next entry?
0.
0. And then always, it's a symmetric matrix, so if the top right is 0, the bottom left is 0 also. And then the bottom right?
6y.
6y. Any questions at all on that? So that tells us our D is equal to the determinant of that, which is 36xy. Because you multiply 6x times 6y minus 0 times 0. Any questions? Any questions on that? The other thing, and I'm just going to write it out now because we need it, is fxx, because remember that helps us classify the critical points. And fxx is 6x. Any questions so far? Okay, so now what we do is we look at our 4 points, and let's start with 10, 5. And if you look at 10, 5, everything is positive. 36 times 10 times 5 is positive, and 6 times 10 is positive. Again, we don't really care about the number. We just care about whether it's positive or negative or 0. So if everything is positive, you remember what the classification is for that critical point.
It's a minimum.
Yeah, we get a minimum. So notice that D is greater than 0, fxx is greater than 0, so we get a minimum. Any questions so far? Okay, now let's do the next one. So now we have negative 10, comma 5. And with negative 10, comma 5, we have D. So again, D is 36xy. If you plug in negative 10 and 5, you get a negative number. And fxx is also negative, which turns out not to matter, but we'll put it there anyway. So if D is negative, what do you know? It's a saddle. Okay, then we have negative 10, negative 5. And if you plug in negative 10 and negative 5, then we have 36 times negative 10 times negative 5, and that's greater than 0. And fxx, if we plug in negative 10 and negative 5, 6 times negative 10 is negative. So what does that tell us about this point? Yeah, it's a maximum. Okay, and then finally, we have 10, negative 5. And for that one, we get D is, well, if you plug in 10 and negative 5, 36 times 10 times negative 5 is clearly a negative number. So that's less than 0. And fxx doesn't matter, but I'm just going to do it anyway. And that one is also less than 0. So if D is negative, just like we had before, we get a saddle. So this has 2 saddles, a minimum, and a maximum. Any questions at all on working out this quiz?
Is it that they don't matter because it's less than 0 for D?
Yeah, that was just part of the kind of the result, the theorem. If you remember, or even if you don't, it doesn't matter. I didn't prove the theorem. This is one of those where you just trust it. Sound good?
Yeah.
I mean, I could prove the theorem, but I don't think anyone would understand my proof. So it's pretty complex. So at this point, again, there's just 4 things. If D is greater than 0, then you either have max or min. It's a min if fx is greater than 0. It's a max if xxx is less than 0. If D is less than 0, you always have a saddle, no matter what fxx is. And if D equals 0, you know nothing. So in that case, you need to do further investigation. That's all I can tell you. There are other ways of doing it, but we're not going that far. Any questions at all on anything about this quiz? Any questions? Okay, let's go here. And I wanted to first remind you what is coming up in not too many days, in 4 days.
First exam.
First exam, okay? So get ready for that. And in fact, I think I want to do it this way. Just want to show you some stuff. And so a couple things. One is if you look at the syllabus, exam 1, May 15th, and it's 15% of your grade, take it seriously. Okay, so notice that the exam itself is worth all of your quizzes and homeworks combined. So again, the quizzes and homeworks are to give you an idea of how you're doing. The exam is to give me an idea how you're doing. You see the difference? So that I can give you a grade. So that's really important to get that exam, get ready for your exam. The second thing, and I'm not sure if, did anyone notice that there's been a change to the syllabus in the last 40 hours or so? Okay, again, subtle, but see this exam 1, it's now linked. Did no one notice that? So if you click on that, that will take you to a practice exam. And what I did, again, this is the same class that I always teach, but we're teaching it in different orders and test it a little later and stuff. So what I did is I kind of grabbed the practice tests that I used to have. I put in the problems that you need, okay, because not all of them are completely relevant. And so the key, there's actually 2 keys because we used to do this in 2 exams. And those 2 keys are there, but the keys have more problems than you need, but it does have them all. It's better not to look at the key at all until you finish the complete exam. It's always smart. And I'd rather not show you the exam because the idea is study for the exam and then take the practice exam, okay? So you're not supposed to take the practice exam for study tool. You're supposed to take the practice exam to see if you think you might be ready or not. Does that make sense? So you're probably not ready for this practice exam because you probably haven't studied that much yet, but you should study pretty soon. And then you take the practice exam, and the exam on Friday includes everything up until through what we're doing today. So up through Wednesday's homework. So you're not quite ready for the exam because there'll be one problem on it you don't know how to do. Okay, and that is what we're doing today. Any questions at all?
Are we all gonna be taking like at the same time? Is it gonna be set during class time?
Yep. Yeah. I do not. I'm not. I know this feels weird. It doesn't. I'm not treating this like an online class. I'm treating like this a regular class at which we're forced to do lectures online. Does that make sense? And tests, which is different than an online class. An online class, I can't expect people to be able to make it at the same time. But in this class, I can because you signed up for this time. Sound fair? So, so it will be timed in the whole bit. And what I'll do, I don't even know if I did that yet, but I'll set it at, it's going to be set though, unlike the quizzes, it'll be set for the beginning. So 8:30, not 8:35. Okay, and you don't want to go to Zoom because if you go to Zoom for your regular exam, while you're doing the regular exam, one thing it'll kick you off. The other is there's going to be all kinds of issues with possibly with your computer because Zoom is a big RAM suck. And so is Proctorio, and the combination of the 2 of them might destroy your, might, nail your computer. So you just want to go to the exam. Okay, and I'll be around before the exam in case there's any questions. A little bit before. I mean, it's 8:30 in the morning, so but I'll make sure I'm around a little bit. Any questions at all?
Yeah, so there's no way during the exam to ask you a question then?
I don't think so because with Proctorio, you're not able to leave the screen.
Mm-hmm, right. Okay.
And it's a tough one. I'm I'm sorry. I don't know if you have suggestions. I don't know what else I can do about it.
Yeah, I know it's kind of tricky.
Yeah.
And then another question, I don't know if someone's already asked this, but are our quizzes like available to go back and like practice with?
Yeah. And what I'll do, there's a couple that probably aren't, because the idea is they're not until I reopen them up. Does that make sense? Most of them are reopened up, but I think last week's I may not, and today's obviously.
Okay, so just
So
like
I'll
the
do that
reopen
today.
ones.
Yeah, so
Okay.
most of them are open, and then the rest will be open by the end of today.
Okay, cool.
Yeah, and actually, that's a really good question. It's a better question than you can imagine, because the quizzes I think are even better practice problems than the practice exam. Okay. You know, separate part. No, I can't do separate parts of the exam. It's a proctorio issue. So this is one of those where the whole thing is done without using a computer calculator. And I'll make sure they all can be done. So, you know, it's kind of like the one we had today. You didn't need any kind of calculator for that. I mean, I hope you can all take the square root of 100 without a calculator. Okay. But I think there's a scientific calculator available on Proctorio, at least to do that kind of stuff. Take you forget the square root of 100. Yeah, this one's all on computer. You can write on the table, but the problem is that your solution needs to be put in the computer. So if you need to write on the table to visualize something, you can do that, you know, wherever we're working, but your solution is into the computer. Again, I'm doing my best. There's no great solution to any of this. I really hope we're back in fall. Right now it doesn't look like it, but I don't know. I can at least be hopeful. I don't think this is the best, but I'm just doing what I can, and hopefully you understand that. So let's see how fall is. Yeah, you won't have access to email. Yeah, you don't have access to email, so that doesn't work. You cannot just email me anything because Proctorio blocks everything except the test. And once the test is over, then emailing me isn't really enough because then you can go in and look at other stuff on your computer. And that's the whole point of Proctorio, is it blocks everything else you're doing and watches you. So sorry about that. Again, there's no great solution, but I have to do what I have to do. Okay, any other questions before we start and talk about constrained optimization of multivariable functions?
Would you mind extending the homework that's due today till 1 o'clock?
Any extensions need to be personal and not for the whole class. Unless
Okay. Well,
unless there's something like, if we had an earthquake and our electricity just died, that's different, like the whole town. But I don't think anything went on in the town that I need to extend for. So that needs to be, if there's an individual reason, that's different. Does that make sense?
yes.
The homework last night was just a little bit tough, though. It was quite long, too.
Yeah,
Yeah, I've heard
it was
super part.
crazy.
It was crazy. Okay.
I had to work, like, I didn't even have time. And it was, like, Mother's Day, too, so...
Yeah. Sorry. Yeah, believe it or not, I copied it from Bruce. I don't want to say you should blame Bruce, but that's what I did. So I just grabbed Bruce's homework and popped it in.
Talk to
Sorry
him
about
about it later.
What's that?
I'll talk to him about it later.
Yeah,
Yeah,
no,
we're
don't
gonna
do
have a
that.
discussion.
Don't make him the bad guy. Okay, shall we talk about new material? Unless you have something else? Okay, so let's talk about new material. The interesting thing is, this is especially important in economics. I know we have at least one person in econ. And in fact, in econ, econ people have to take calculus, but the whole point of the calculus class, for especially after the first quarter, is to get to Lagrange multipliers as fast as you can, because it's so important in econ, and that's the only important thing there is in econ, basically, for calculus after first quarter. So it's kind of interesting. So, but it's also important for engineering and other things too. And that's Lagrange multipliers. And the idea here is that a lot of times you have a function of 2 variables or 3 variables, whatever. And that function in econ, it would probably be profit or revenue or cost. Okay, those are the 3 main things that people care about. And in engineering, it could be all kinds of things. It could be energy that you need to run your vehicle. It could be, I don't know, entropy or whatever, enthalpy or something like that. And you often want to find the max or min, but there's going to be a constraint. So for econ, the constraint might be that you only have, you know, a fixed amount of materials and supplies to get your business done, and you want to find the best way of getting that business done to make profit. In physics, then you usually have things like the conservation of energy. You guys all seen the conservation of energy in physics as you've had physics?
Yeah.
Yeah. So when you have conservation of energy, that means that the energy itself is a constraint because you can't use more energy than you have in physics, right? And similarly, you can't end up with more energy, less energy than you have. So that's a conservation of energy issue. So a lot of times you want to find a max or min to deal that includes constraints, whether that might be, again, the amount of, you know, materials and people you've got and overhead and all that kind of stuff, or it might be some kind of conservation law. Those are the typical constraints that happen. And it comes up all over the place. This isn't one of those kind of once in a while applications. This is a main application. So what you have is you want to maximize something or you want to minimize something that is a function of 2 or more variables, and you have a constraint. Does that make sense in terms of the reason why you care about it? All right, so then what you want to say is, well, the constraint, maybe I'll even draw a picture. These pictures are hard to draw, though. So your constraint might be some, let me do a scribble. Your constraint might be you have to stay in this region here. So inside what I just drew. Any questions so far? Okay, so that's the constraint. And your function, a lot of times you want to think about the function, especially if you're going to be drawing it in 2 dimensions, is we'll draw the level curves. So let's do level curves for the function. And let's do that, and how about red? And the level curves might look like something like this. Maybe I'll do one more. Whoops. That wasn't a good one. Right in between there. There we go. Okay, again, I'm doing my best on the drawing. Oh, the scribble didn't. I want to get that one. I want to make that one not red. That was the whole point. There we go. Okay, so the constraint is going to be in black and everything inside that black area. And the level curves will be your function. And what you want to do is you want to maximize or minimize the function. And in particular, I'm not putting numbers in because they might go up or they might go down. Either way, it's going to be the same story. So first thing is like way out here. That's not allowed. Does everyone understand that? Where my arrow is, that's not allowed. And why is that not allowed?
It's not inside our bounds.
Yeah, it's outside the bounds, so that can't be where the minimum is or the maximum. Okay, so let's suppose these level curves are going up as we go. So if the level curves are going up as we go, then this central one cannot be the maximum. Okay, because the next one is bigger. Do you see that? And it turns out that what you want to do is you want to say, well, we're looking for the maximum, and where might that be? Does that make sense? Well, it turns out that the maximum is always going to be, and the minimum, by the way, at such a point so that the gradients are in the same direction. And there's a reason for that. If you have the gradient in the same direction, then what do you know?
You have no max or min?
No. You do have a max or min, but that's going to be that critical point of being the max. Remember, this is not local max or min. These are global max or mins. Does that make sense? So that means if you go out a little bit, that's bad because then you're outside the region. If you go in a little bit, then that means you've lowered or up higher it. Does that make sense? So that's the big rule of Lagrange multipliers. So that's kind of the idea. And whoops. There we go. So that gets us ready for our big theorem. And the theorem basically says what I just said. So let me write it out. And this is, again, the big theorem of the day. And for econ people, this is actually the biggest theorem in calculus for this quarter. No question about it. Okay. And for others, it's still big. So it says let f of x comma y be differentiable. Can't really do anything unless you have differentiable. And g of xy equal some constant to find a smooth curve. Notice that f of xy is a function of two variables in the three-dimensional space, whereas g of xy is a function of two variables, but it sits in a two-dimensional space. Okay, then the max and min, and I'm going to write global max and min. Of f subject to the constraint g occur when and I think I need to make it look pretty. Grad of f is equal to some constant, and the constant everyone uses is that guy. Do you know what you call that one?
Lambda.
Lambda. So lambda times grad of g. So the gradient of f is a constant multiple of the gradient of G, okay? Which is another way of saying that the vectors, gradient of F and gradient of G, have the same direction or opposite directions. It can be multiplied by -1, 2. Okay, any questions on the big theorem? Let me do some highlighting, because this is the biggie. I want to make it bigger because it's so big. Then let's put it in red just to like shout it out. This is the biggie. This is really all we're doing today. Any questions on what this says? Okay, so what this allows us to do is find global max and mins a lot easier than the way we did it on the homework due today, which might be why some of the homework took you a long time, because the problems are long if you don't have Lagrange multipliers, okay, which is what this is. And you'll find out that these can be long too, but not as long. This almost always makes it nicer. So any questions at all? Okay. Let's see. Maybe I'll hold off. Do you guys want to see the proof or not? I'll let you choose. Or would you rather see more examples?
I believe you.
You believe me? Yeah. It's in the book too. And
I mean,
it's
will
on the
this
internet.
make it easier to understand?
The proof? Probably not.
Then no.
Okay. But it'll make it so you believe it. You know what I mean? I don't think we have any math majors in this class. If math majors definitely don't need to see the proof. But econ majors, engineering majors, physics majors, they don't need the proof. Okay. But there's a proof, and I'm not gonna write it all out. But basically, what you do is you say you have this g of x, y equals c, right? And that's a curve. What you do is you parameterize the curve with an x of t and a y of t. And then you write it as parameters, and then you show that it works. Okay. There's some work to do on that. Not too bad, but a lot of typing too. Okay. So more importantly is, how do you use something like this? Okay. So let me give you an example, and we'll do more than one example.
What does lambda represent again?
Lambda is a number.
Okay.
Yeah. And the reason why they use lambda is it's named after a guy named Lagrange. Okay, because Lagrange is the guy that figured this stuff out. And L is a terrible letter as a constant because it looks too much like a 1. So they use the Greeks. So does that make sense? That's the reason why they stuck with lambda. And everyone in the world uses lambda. I've never seen any book that says anything other than lambda. So I want to be consistent with the whole world. And I don't want to say, well, I don't like that letter, so I'm going to use A or something.
What is the G in gradient?
You
just a
mean
different
inside the parentheses?
function?
That's important. Okay, that's not just some letter. That is the constraint. So the
Okay.
idea is, like I said, in econ, for example, you may be in the case that you have 2 warehouses, and maybe you have 2 different products, and you're gonna have to decide, how much of each product should each warehouse make. Does that make sense? And the total amount of stuff the warehouse can make is going to be fixed. Does that make sense?
Yes.
So G will be the equation that says that you can't make more than a total amount of stuff. Does that make sense?
Yes.
And F will be the profit. And what you want to do is you want to maximize that profit given the fact that you only have the 2 warehouses. Okay, so that's kind of the econ way of thinking about it. Okay, the physics way of thinking about it is G will be the energy that you have based on maybe electromagnetism and gravity. That maybe there could be other forces, but based on those forces have to be fixed. And then you want to say, what is going to be the maximum amount of velocity you might get based on those things. Does that make sense for the physics type? Yeah. So again, these have real applications. And once I do one, then you'll see what you can. So let me give you an example. Okay, and it is find the extrema of f of, write this in the equation, f of x comma y is equal to x squared minus y squared. Okay, and then there, subject to the constraint y minus x squared equals 0. Any question on the question?
Can you scroll up?
Yeah, that I can do easily. So notice we have this function of xy, and that's x squared minus y squared. And by the way, because this is important for Friday, is what is the name of the surface? Because I could ask something like that. Who knows how to say what that is? Okay, it's not a sphere. A sphere would have to be x squared plus y squared plus z squared equals a number. And this definitely isn't that. There's minuses and there's no
Is
square
that
on the end.
a paraboloid?
Yeah, that's a paraboloid, because notice that, and it's a hyperbolic paraboloid, to be more exact. Does that make sense? Because if you hold x constant, you get z equals negative y squared, which is a parabola. If you hold y constant, you get z equals x squared, which is a parabola. If you hold z constant, you get x squared minus y squared as a constant, and that's a hyperbola. So that's why it's a hyperbolic paraboloid. Any questions on that? Okay, you don't have to know that for this question, but any chance to give review when there's a test coming up. All right, and so it's saying that we have this hyperbolic paraboloid, but we're only going to be allowing points such that y minus x squared equals 0, which, by the way, is y equals x squared. So on that parabola in the xy plane, we're going to look at the paraboloid, the hyperbolic paraboloid, but we're going to restrict it to being above this parabola. Any questions on that? Okay. Okay, so first thing to note, just because this is easy, I hope it's easy for everyone. Are there any points of discontinuity or non-differentiability? Yeah, it's supposed to be easy. I hope that was an easy question. These are all polynomials. Polynomials are like the best thing you could ever ask for. Okay, so there's no problem with discontinuity or anything like that. If there are, then you got to be careful. Okay, so then what we're gonna do is we're gonna use Lagrange multipliers. And let's do that. So what we need to do is you need to find grad of f. And what is the gradient of f? Not supposed to be that hard. Yeah, it's 2x comma negative 2y. And let's find the grad of g. And what's the gradient of g? Yeah, negative 2x1. Any questions so far? Okay, so now we're going to use the Lagrange multiplier theorem. And I'm going to say, and since I'm going to use a lambda, I need to insert 2x comma negative 2y is equal to lambda times negative 2x comma 1. Any questions so far? Okay. So what we get now what we can do is we can put this together in two equations. What's the first equation without vectors? All right, there's a lambda times negative 2x, but it's an equation, there's an equal. It's 2x is equal, actually I need to do it in the equation. 2x equals lambda times negative 2x, or negative lambda times 2x. Oops. That one more time. So that's again 2x equals negative lambda times 2x. And we also have negative 2y is equal to what?
Lambda.
Yeah, lambda. What's the problem here? Why is this not sufficient? Yeah. So here's the thing. There are three equations. There's not two equations, there's three equations. What's the third equation? Anyone see it?
Is there one for Z?
There is no z here, actually. We just have x, y, and lambda. Okay, it's actually there, but you have to notice it. And it's y minus x squared equals 0. Because that's an equation. That has to be true because it's a constraint equation that has to be true for the solution to be correct. So that you do the equations based on your Lagrange multipliers and the constraint equations. And now we have three equations and three unknowns, which is much better when you're trying to solve, because then we'll actually get something. Any questions at all on getting this set up? Okay, so now again, we have three equations, three unknowns. And as you're probably used to, the hardest part about this whole topic today is any guess? Algebra. Yeah, exactly. Algebra. That is so classic in calculus, right? Calculus is not hard. Algebra is hard. Of course, I gave you an example that's not too bad. There could be some really evil examples where you're going to have three equations that are nonlinear with three unknowns, and they're not solvable without some kind of numerical method technique to get an approximation. And that's pretty typical of real life problems. Okay, it's not typical of problems you can get on tests, but it's typical of real life problems that you're going to have to use a computer to solve the three equations, three unknowns. And you're not going to get an exact answer. You're going to get however many decimals you need. That's really typical. And then again, you have to do even higher level math to understand how do you make it efficient so you don't crash your computer. Just let you know. So there's all kinds of issues with Lagrange multipliers, but the issues are not the calculus, they're the algebra, because solving equations where they're not linear is hard, okay, which you're all used to. But the good news is this one's not hard. So my recommendation that most of the time works when you're doing Lagrange multipliers in a calculus class is you solve for lambda in both the first two equations. So the first equation, get a little water because I'm losing it. So the first equation becomes lambda equals negative what?
1.
1. So that's very nice. So if you can get lambda, then the rest is going to be very nice. Let's put it in. So lambda equals 1. Okay. That equals negative 1. Okay. Because if you divide by negative 2x, you get negative 1. All right. Once you have lambda, we could take that lambda and put it into our second equation. And then we can get y. So the second equation gives us that negative 2y equals negative 1. So what's y?
1/2.
Yeah, y is 1/2. All right. Now that we have y, now we can get x. Because we know that y minus x squared equals 0. So now we can say one half minus, actually let's make that a nice 1/2. Because I can. Minus x squared equals 0. Any questions? Any questions? Okay. Well, can we get x now?
Definitely.
Okay. Well, 1/√2, but that's not the only answer.
Plus or minus.
Yeah, there's two. There's positive 1/√2 and there's negative 1/√2. So now we actually have the full solution. Let's do it. So now we can say that the points are going to be at x equals negative 1/√2. Let's go negative first. So 1 over the square root of 2, because that's our x, comma, and y is 1/2. Comma. And now I'm just going to, hopefully this will work. Copy and paste. Get rid of the negative. Oops. I wanted to get rid of. That's better. Comma, positive 1/√2, comma 1/2. Any questions on that? Okay, how do we decide about max and mins now? Yeah, now we got to plug in and see what we get. Okay.
Do we plug it into our constraint?
If we plug in the constraint, we'll just say true. Do you see that?
Yeah.
Because that's how we use a constraint to get this.
Mhm.
So it better be true. So we plug it into our f of xy.
Okay.
And it turns out if you plug it into the f of xy, what do you notice about the 2 points? Okay. Same, different sign. A little confusing. Okay. And even better, they're just the same. No different sign. They're the same. If you square negative root 1 of negative 1 of root 2, that's the same thing as squaring 1 over root 2. Okay. So in particular, let's write this out. F at either of these points is equal to what? Well, if you take 1 over root 2 squared, you get a half, minus a half squared is minus a fourth. A half minus a fourth is
A half. Or fourth, sorry.
a fourth. So that means f is a fourth. Okay. Is that a max or a min?
Wouldn't it be a minimum because it's concave up since it's positive?
No, we can't do that. We're not using, don't go 2 days ago because that doesn't work. We're not doing Hessians and all that kind of stuff because now we have a constraint. So here's the idea. Just looking at the constraint, is it clear that 0, 0 is on the constraint?
Yeah.
So if you plug in 0, 0, you get 0. Well, a fourth is bigger than that, isn't it? Is that clear? So that means this must be a maximum. So the maximum is 1 over 4. Any questions on that?
Is it a point or like could we or is it just
So
1
if you
4?
want, you could say the maximum is 1 over 4, which occurs at the point and I don't want to retype this whole thing, so I'm just copy and paste at these points. So there's 2 points at which the maximum is 1/4. So they're tied. Does that make total sense, or is that a little confusing?
No, that makes more sense. Thank you.
So again, it's kind of 2 ways of looking at it. Are you interested in, like in economics, are you interested in how much money you're going to make? Or are you interested in how much work you're going to have to do at each of the different warehouses, for example? So the how much money you're going to make, that's the maximum. The how much work you're going to have to do at each warehouse, that's the point. Any questions on that? Okay, so again, this is an example, and there it is. Okay, ready for another one? And the next example is find the distance from the origin to the surface XYZ equals 8. Okay. So what does it mean to even say find the distance from a point to a surface? No? What does it mean to say find the distance from the origin to the surface?
Should we be using?
Find the, oh,
Find a vector, not a vector. Definitely not a vector. Distance is a number.
it's the
Use a
square root of
level
x
curve.
squared.
Okay, so let me explain because I'm getting different interesting things. It's saying find the minimum distance from the origin to all points on this surface. Because every point in the surface basically going to have different distances. Does that make sense? And we want to find the smallest possible distance from the origin to this surface. Any questions on that? All right, so the first thing, and this is a typical trick, but it's a very convenient trick, and I recommend you learn this trick. And that is, we could use the distance formula, but better is let us, instead of finding the minimum distance, let's find the minimum squared distance. Why is it easier to find the minimum squared distance? Yeah, square roots are no fun with calculus, right? All kinds of messy stuff happens. So if we find the minimum squared distance, and we can say that d squared, and use capital D squared, so it's distance, not derivative, is equal to, well, that's going to be, it's from the origin, so it's going to be x squared plus y squared plus z squared. Any questions on that? Okay, and now what we can do is we can use Lagrange multipliers. I didn't write this down in the theorem, but the theorem works for however many variables you've got. I just wrote it for 2. It works for 3 also. So what we can do now is we can say the gradient of our d squared function. That's easy. That's 2x, comma 2y, comma 2z is equal to lambda, some constant, times the gradient of the xyz function. The xyz function is yz, comma xz, comma xy. Have I lost anyone? Okay, I can take this and turn this into 3 equations. And we could say 2x equals lambda yz. We can say 2y equals lambda xz. And we can say 2z equal lambda zy. Wait. Is this right? That shouldn't be zy. That should be
Why?
xy. That should be xy. Better. So lambda xy. And we still have xyz equals 8. So now it's 4 equations, 4 unknowns, but they're not too bad. So there's all kinds of ways of solving this. What I recommend is solve for lambda. Okay, and we can even do better than that. we can solve for lambda xyz. So what I can do is I can multiply left and right on the first equation by x, second equation by y, third equation by z. And then all three right-hand sides will be lambda xyz. And when I do that, I get 2x squared equals 2y squared equals 2z squared. Any questions on that so far?
What did you do?
So what I did is I multiplied the first equation by x on left and right, the second equation by y on left and right, and the third equation by z on left and right. And the reason for that is that way the right-hand side is always lambda xyz. Tricky, right? But that's called algebra. Algebra is tricky. Okay, so that means that x, y, and z are all plus or minus of each other. So I can say that x is equal to plus or minus y, which is equal to plus or minus z. Because if x squared equals y squared, then they're plus or minus each other. So now what I can do is I can pop this into the third equation. And I can say that x cubed equals 8, or plus or minus x cubed equals 8. Because if they're all the same, but maybe different signs, I just get plus or minus x cubed. So that says that x equals plus or minus 2. Have I lost anyone in the algebra? Do you agree the algebra is a lot harder than the calculus?
Yes.
Taking a derivative of x squared is a lot easier, I think, than solving 4 equations and 4 unknowns. Okay, and by the way, I'm not going to write this out, but x, y, and z are all plus or minus each other, which means y and z are also plus or minus 2. Okay, and you have to make sure that there's an even number of minuses. Okay, which doesn't really matter that much because I want to find distance, and the distance squared is x squared plus y squared plus z squared. That means our distance equals, well, x squared plus y squared plus z squared, and that's just going to be 2 squared plus 2 squared plus 2 squared, which is
12.
yeah, 12, and that's d squared, so d is root 12. And there's our distance from the origin to the source. Did I lose anyone there? Okay, now comes a next extension. So now let's do another example. And that is maximize f of x by z is x squared plus y squared plus z squared. So same idea. Ah, what happened? It's over here. Plus y squared plus z squared subject to the two constraints. And that's going to be x, y, z equals 1. And x squared plus y squared plus 2z squared equals 4.
Can you scroll up?
Yep.
Thank you.
Okay, so any questions on this question? So now we have two constraints. So in econ, by the way, the constraints typically are, any guess?
Expense and and profit, maybe? I don't know.
Profit's profit's never a constraint. You're always hoping for a whole lot of profit. It's an expense and labor, right? People and capital are the typical two constraints. In physics, the constraints could be gravity, the amount of gravity versus the amount of electromagnetism, something like that. A lot of different things that can happen in physics. Okay. So I'm going to do this one because we don't have time to fully derive a theorem about it. So I'm going to explain the theorem as I go with an example. And you'll see it's not that much different. And the theorem says what I do is I just extend Lagrange multipliers with a second constraint. So what I'm going to do is I'm going to take the gradient of f. So I'm going to do this in general first, and then we'll compute. Grad of f is equal to lambda times grad of g. But what's the problem if we just stop there?
We have two constraints.
Yeah, we have two constraints, which would mean we have two different gradients. Okay, which means we need the next letter. Who knows the next letter of the alphabet?
H, right?
No, mu. Right, after L is M, so after lambda is mu. So mu times the grad of, oh, that was the H you're talking about.
Yeah, sorry, our alphabet.
Yeah, that one, I hope all of you know the letter of our alphabet. But the next letter of the Greek alphabet after lambda is mu. Okay, so that's going to be the key equation that's going to deal with two constraints. Okay.
So we literally just said, all right, here, add another constraint.
Exactly, because the class example says here's another constraint. Do you see? So what the generalized theorem says is the gradient of f is the summation of ci times the gradient of gi. So if there were 10 constraints, then there'd be 10 different constants and 10 different gradients on the right. Does that make sense?
Yeah.
I'd never give that to you on a test with 10. Way too messy. But in real world, it happens sometimes. Okay, but definitely not a test. 2 is as many as I'd ever give you. Okay, so now we just do it. So I can go equation. And let's make vectors. Gradient of f is 2x, 2y, 2z. That's not supposed to be hard for anybody. I hope not. And that's going to be lambda times the gradient of g, which is going to be yz, comma, xz, comma, xy, plus mu times the gradient of h, which is 2x comma 2y, comma 4z. Any questions on this? Okay, so how many equations, how many unknowns are we going to have?
3 equations, 5 unknowns.
Got the unknowns right. 5 equations, 5 unknowns. Because don't forget the constraints. The constraints are always equations. So what we're going to get is 2x equals lambda yz plus mu times 2x, or 2 mu x, and then we're going to have 2y is equal to lambda xe, and then plus 2 mu y, and then we'll have 2z is equal to lambda xy plus 4 mu z. And then we're also going to have x, y, z equals 1. And we're going to have x squared plus y squared plus 2z squared equals 4. Any questions on this? Okay, are you convinced that the algebra gets pretty darn evil? Okay, algebra can be really hard. So here's an example: 5 equations, 5 unknowns. They're not even linear. It's messy. Can this be solved? So can this be solved?
It can be.
Mm-hmm. And you all know how to do it, right?
I'm sure we have the tools.
Yeah, so we're going to do the same idea as the last one. Is we're going to take that first equation, we're going to multiply it by x. Second equation, multiply by y. Third equation, multiply by z. Okay, we're about 4th and 5th at the end. Any questions on that idea? And then we can get rid of the lambda yz, and the lambda xz, and the lambda xy. So I'm going to do that. It's a lot easier to watch me do it, by the way, than try to do it yourself. So when you do that, we have lambda xyz is going to be 2x minus 2x squared minus 2 mu x squared. And the second equation is going to have the lambda xyz, and that'll be 2y squared minus 2 mu y squared. And the third equation is going to multiply by z, and you're going to get 2z squared minus 4 mu z squared. Any questions on getting those? Any questions on that? Okay, what do we do from there?
Factor out of 2.
Yeah, you can factor out a 2, and I'm actually going to factor out a whole bunch of stuff. I'm going to factor out the x squared, the y squared, and the z squared also
Okay.
individually. So now I can say that 2x squared times 1 minus mu is equal to 2y squared times 1 minus mu, which is equal to 2z squared times 4z squared. Now 2z squared, that's right, times 1 minus 2 mu. Any questions on that? All right, well, the first equation there tells you x is plus or minus y. Just divided by 1 minus mu. Any questions on that? Okay. And did I make a mistake? I might have made a mistake in the original writing of the question. Okay, but then we got to do more. What else can we do for the second equation? The second equality. So for the second one, let's play around with that one. I want to even leave it with the 4, multiply the 2 through, but that's okay. So what can we say? So now we can get rid of the 2 and we can say x squared we're running out of time, so I don't know if I'll be able to finish this. These are long though, as I think you're figuring out. So x squared times 1 minus mu is equal to z squared times 1 minus 2 mu. Okay, I'm about out of time, so I think I'm going to give you the punchline. And that is, you can find it. Keep going and do more algebra and find the answer. I just looked at my clock and it's time to be done. So I need to be done. I don't want to go too much over, but you get the idea. You do a lot more algebra and then you go through it. Okay, so if you have a constraint optimization at which there are 2 constraints, you can have a lambda and a mu and expect it to get really messy. So I need to stop my share. And let's stop the recording.